In the previous section, you wrote a simple test for your blockchain in Substrate. In this section, you'll change how your network prioritizes various transactions, and you'll learn how to handle an annoying UTXO race condition that Bitcoin also experiences. Specifically, you'll learn how to change the blockchain transaction queuing logic, and it turns out you can do so in Substrate without much code. Consider the following race condition that currently exists in our implementation. Suppose Alice sends Bob a UTXO transaction, spending her UTXO A to create a new UTXO B for Bob. What's happening behind the scenes is that Alice's transaction starts to immediately propagate across various nodes in the network. And almost immediately, Bob also decides to spend his newly received UTXO B to create a new UTXO C. And immediately, his transactions also starts to propagate across the network. However, a lot of the nodes that are hearing from Bob might not have heard from Alice yet, due to regular network latency issues and other real-world constraints. These receiving nodes will thus reject Bob's transaction, since to them, UTXO-B doesn't yet exist. But from a use case perspective, Bob's transaction is valid. So these nodes rejecting Bob's transaction and erroring him out is not an ideal situation. Ideally, we can queue valid transactions that are just pending race conditions to be satisfied in something called the transaction pool. You can think of the transaction pool as a blockchain's queue that contains all of the network's currently unconfirmed transactions. Within the transaction pool, multiple verification steps, among other networking logic, are constantly being executed. In particular, in Substrate, we can invoke something called the tagged transaction queue, which is an API trait that lets us interfere with the blockchain's transaction queue. Within that, we can check for something called transaction validity via a struct called valid transaction, which again gets checked before any transactions are executed. This runtime API lets us wrap transactions into valid transaction types that have multiple properties, like the priority, which designates the order that transactions can precede each other. For our implementation, this actually seems like a good place for us to make use of our reward total, which, if you recall, is the remainder amount from each UTXO transaction. We can let higher reward transactions have a higher priority in the transaction pool queue. Requires is a vector of prerequisite tags that must be satisfied by a previous transaction before this transaction is queued up to be processed. Its complement, provides, is a vector of tags that are fulfilled from a particular transaction, likely satisfying the requires tags for a consecutive transaction to follow. Clearly, this seems like the place where we should address our race condition problem. And for the transaction tags that need to be satisfied before the following transactions can be made, we can just use the hash address of our UTXOs. Next, longevity describes the minimum number of blocks where the transaction can still stay in the pool. And after this period, transactions should either be removed from the pool or revalidated. Last but not least, propagate is a Boolean flag, which lets us indicate if this transaction should be propagated to other peers. The default setting for this would be just true. Let's go ahead, flip back to our code editor, and implement what a valid transaction could look like. Now let's go into the lib.rs file for the first time. You can think of this as the root file for our entire UTXO runtime package. Above the fold, you can see a lot of the other modules that take care of consensus and other blockchain infrastructure requirements. Scrolling down a bit, this construct runtime macro is quite key. It constructs your blockchain runtime with the given modules here. Notice that I've already included the UTXO module that we just made in UTXO.rs as one of the runtimes to be constructed. Module, call, storage, and event are actually the new structs and enums you've created inside the macros declare storage, declare module, and declare events. For example, for module, coming back to UTXO, you can see that you've implemented it here, as well as declaring this new enum call, which you've also inserted here. So here's how that ties together. By including them here, by including the variables here, we're telling the construct runtime macro to go ahead and build the declare module, declare storage, etc. macros we implemented in UTXO.rs. Scrolling down further, we see another macro, this time called implement runtime APIs. We'll want to implement our valid transaction check within this scope. So let's go ahead and invoke the tagged transaction queue API by implementing the following. So we want to do implement from the SP transaction pool, reaching into the runtime API, and getting the tagged transaction queue API of type block for this particular runtime. So far this is consistent with all of the other implementation extensions that you see up here. Now at this point, specifically, the default function we want to override is called validate transaction, which has the following function signature. Taking in transaction as an input, where the input is of type extrinsic. Now in the Substrate ecosystem, transactions that are being sent by external users to the nodes are called extrinsics. And this function signature returns the transaction validity struct, which will contain all of the required flags that will be checked to see whether or not this transaction needs to stay in the queue further or if it's ready to be processed. The default action here, if we didn't try to re-implement this function for the spend extrinsic, is actually the following expression. From the executive palette, we simply run validate transaction, passing in the input transaction. And this will still be the default case for the majority of extrinsics that come into the transaction pool. Now what we want to do here is match only the transactions which are coming into the queue where the transactions are exactly the UTXO spend function call that we created in UTXO.rs. So we only want to match on the transactions where users are trying to spend UTXO. So to get the transaction that's actually occurring, we get to use a Substrate function called isSubtype, which you can access with the following syntax. Now that we've retrieved this incoming transaction, what we want to do is actually match it to see if it's of type spend function. So if let sum, where within sum the value that we're matching for is from the UTXO palette as one of the call functions that we designated, specifically the spend function. Another thing I want to do here is type ref transaction. This is Rust specific syntax, and it basically just lets me do any pattern matching or destructuring via this let binding that I want to do. I'm using this ref keyword here so that we can take references into the field for what's returned here, giving me access to this transaction variable within the scope of this if let function that we just created. So now that we're getting the actual transaction object that the user is trying to pass in, we want to match the transaction for the three possible cases we discussed a few minutes ago. The first case is, of course, the error case, where, going back to our spend function, we know that we're getting a dispatch result. So the error case will match for the cases where the transaction was not valid and a result of error was returned, halting the transaction. We'll also need to match for the race condition, as well as the third valid transaction scenario. So how do we do that? Well, recall at the earlier part of this tutorial, we implemented a validate transaction function. So going back to our UTXO.rs file, we find it here. Recall that this validate transaction function returns a result, which could be an error or the value of the reward. The elegant thing to do here is to actually extend this existing check we've already implemented to check for the third race condition. So in here, what we'll want to do is, rather than just having this function return the reward value, we should return a struct of type valid transaction. Recall the valid transaction struct from reference documentation looks something like this. So if we were to get this struct back from our UTXOs validate transaction function, then we can easily take care of cases 2 and 3 within one expression. Now, something to take note of is that the UTXO validate transaction is named the same as this default validate transaction, but they are very different functions. So just remember that as to not get confused. Okay, so let's go ahead and implement matching this transaction on the potential 3 cases that might occur, assuming that we've already modified our UTXO validate transaction. The match statement is as follows. Let's match by invoking the UTXO module, the validate transaction function, again, different from the function up here, by passing in this transaction variable that we're getting in from this reference. And the potential return variables from this function include an error containing error message E, in which case we'll do something. And then the other possible return variable is an OK, which, as we've just spoken, we will re-implement to return a valid transaction type. Let's name that variable VT, in which case we'll do something else. Okay. Coming back to handle the error condition where our transaction verification has failed. Well, first we want to print the error message to our runtime console. And immediately after that, we'll want to return an error object as the transaction validity value to signal that this validate transaction function on this transaction has failed. And this is just some custom syntax for us to do some error type conversions. Let's just clean up our implementation a little bit. Okay, for the second and third conditions, our new validate transaction function will still return an OK and contain a valid transaction type internally. Conveniently, what this function signature is currently expecting is exactly that value type wrapped in an OK result. Let's now flip back to UTXO.rs. Coming back to our validate transaction function here, the first thing we need to do is, instead of returning a reward calculation here, this function now needs to return a valid transaction type. This data type has been imported for you at the top of this file. The goal now is to start keeping track of any missing UTXOs in the transaction input and add them to the requires flag for this valid transaction. And at the same time, let's not forget that for every transaction, we'll also need to start tracking the provides flags, namely the new UTXO hashes that get created with this transaction's outputs. And lastly, let's not forget that we now should save the rewards total calculation as the valid transaction's priority number. Let's go ahead and define some variables to keep track of everything. First, let's define a mutable vector to keep track of any potential missing UTXOs in a potential race condition, which we instantiate as a new vector. Next, we need to keep track of the outputs. Let's call this vector new UTXOs. Also instantiated as a new vector. And let's keep track of a reward value up here. So now coming back to our previous implementation, where we iterate through the vector of transaction inputs. At one point, our implementation checks for whether or not that input exists or not. We're now ready to implement the case for where this current transaction's input UTXOs don't yet exist within the UTXO store. Well, in this case, we simply want to push this missing UTXO hash into the missing UTXOs vector that will make up the vector of required flags for our valid transaction. So specifically, we'll be pushing in input.outPoint, converting it into fixed bytes format as a vector. And similarly, as we iterate through our desired transaction outputs, we can now add to our new UTXOs vector. So at the bottom of this loop, let's do new UTXOs dot push, and let's push in this hash in fixed bytes format. Consolidating the bytes into a vector. At this point, we'll actually need to enclose this reward calculation into a check, because we only want to calculate rewards in the scenario where missing inputs is empty, i.e. all of the required input UTXOs already exist and that there's no race condition. Otherwise, we actually want the reward for this transaction to remain at 0, because the validators aren't going to process it anyway. And finally, instead of returning a reward value, we're now ready to return a struct valid transaction with the following fields. The requires flag will simply be the missing UTXOs vector. The provides flag will be this new UTXOs vector that we've created. As mentioned above, priority will now be the reward with a simple type conversion into a U64. And in terms of longevity, we can optimize this to be more efficient later on, but for now, it's easiest to just default it to the max value. Meaning if there is a race condition, some transactions could be potentially stuck in the queue for a very long time. And lastly, let's default propagation to true. And that should work. So coming back to our spend function, this is the one last place where we need to update things, because we're no longer expecting a reward, but a valid transaction type. So let's modify this expression to expect a return of valid transaction. And from this valid transaction, we can still derive the reward by doing valid transaction dot priority. converting it into a value. So at this point, let's flip back into our console and run the simple test that we created a short while ago to make sure that everything still compiles and our refactoring hasn't introduced any new errors. Let's run cargo test-p UTXO runtime. And as expected, I have a few more typos, starting at line 165. This should be new UTXOs, and this should say propagate, not propagate. I think I have another typo in here. Instead of TV, it should be VT. Freudian slip. Let's check again that everything compiles, and our tests should hopefully still pass. So I think one of the reasons I really appreciate that this blockchain framework is implemented in Rust is that the Rust compiler really isn't forgiving, and it often catches a lot of user errors and bugs that otherwise would be perfectly working code, but fundamentally wrong. So in this case, I realized that in my refactoring, I created a new reward variable, but I never actually used it. So rather than instantiating a new reward here, let's make use of the one that's previously declared. In this case, since we're just testing the logic implementation in the UTXO module, regardless of the changes that we make to the transaction queue, our test will still pass. But as we just saw, this is still a helpful exercise in terms of verifying that your refactoring went well. We will still go ahead and test our transaction queue reordering logic in the next section with a UI demo. Okay, this time our simple test passed with just one warning where, that's correct, I don't use this assert error testing macro function, but everything else seems to look good. So we're ready to move on.